Hello everyone, here is another video with OrgTube channel. In this video, I'm going to talk about Bohr atomic models and some practice problems. In Bohr atomic model, hydrogen atom has only certain energy level, or we call them stationary states. As you can see here, energy level 1, energy level 2, energy level 3, and it can be continued by infinity 4, 5, 6, and so forth. Electron must be in one of these stationary state, and it cannot be between these levels. So actually Bohr used the Planck's and Einstein idea about the quantization of energy. So energy of electrons in hydrogen atom can only be the certain values. It can be in level 1, level 2, level 3, and so on. To make it easier, we can draw the levels in this form as well. Level 1, 2, 3, 4, 5, 6, 7, and it can continue by infinity again. Electron in one level can absorb a photon of light and move to the higher level. It can only happen if the energy of photon is exactly equals to the difference between final and initial state. So E of photon should be equals to delta E, which is energy for final state minus the energy for initial state. Also, if the electron exists on higher levels, it can fall into the lower levels and release a photon of light. And again, we have the same equation. The energy of photon should be equal to the difference between the energy of final and initial levels. So by these diagrams, we can explain the line spectra for emission spectra and for absorption spectra. Electron, they can absorb light and move to the higher level and cause the absorption spectra. Also, the excited electron, it means the electron on higher level, they can fall into the lower level and emitting light and cause the line emission spectra. The energy of these levels in Bohr atomic model is equals to negative RH times Z square over N square. Z is the charge of nucleus, and in hydrogen atom the charge of nucleus is 1. So instead of Z square we can write 1. So the energy for level 1 or E1 it's equals to negative RH, that we call it Rydberg constant, times 1 over 1 square. The energy in level 2 is equals to negative RH 1 over 2 square, and so on. To find the delta E, the difference energy of final and initial state, we can subtract two of these equations and we ending up with this new formula. Negative Rydberg constants times 1 over final n square minus 1 over initial n square. If we have absorption, the delta E always is positive. And if we have emission, the delta E should be negative. But if we want to use this delta E for calculation of wavelengths or frequency of light, we only use the absolute value of energy. This equation called Bohr equation. And the value for Rydberg constant it's equals to 2.18 times 10 to negative 18 joules. We also know that the energy of photon is equal to the delta E, and energy of photon can be calculated by h nu or by hc over lambda. Combining these two equations, we can calculate the frequency or the wavelength of the light it absorbs or is emitting in a line spectra. There is another form of the Bohr equation which is called Rydberg equation. If instead of delta E we use hc over lambda, we can rewrite the equation in this form. hc over lambda is equals to negative Rydberg constant 1 nf square minus 1 ni square. And if we dividing both sides by hc, then we have hc here in denominator, and here we will have only 1. The value for RH over hc is equals to 1.097373 times 10 to positive 7. And combining these three constants, we can make another constant, R. So R is for Rydberg equation, and RH it is for Bohr equation. So instead of writing negative RH over HC, we can just write R. And this is the value for R. This is called Rydberg equation. In Bohr atomic model, when we have electron on the first level, here we call it ground state level. And if electron it is in higher level, it's called excited state. Based on the type of transition, we have different series of emission spectra. If electrons fall from higher level to level 1, it means if electron falls from level 2 to level 1, level 3 to level 1, level 4 to level 1, and so on. Then we call this series Lyman series. And Lyman series, they are ultraviolet light. If electrons fall from higher level to level 2, not level 1, like if electron falls from level 3 to level 2, level 4 to level 2, level 5 to level 2, and so on, then we have Balmer series. And Balmer series, it is in visible range. If electrons fall from higher level of level 3 to level 3, so like from 4 to 3, 5 to 3, 6 to 3, then we have Paschen series. And Paschen series is infrared or IR. Let's have some examples for Bohr atomic model. Here is the first question. What is the energy difference between the n equals 1 and n equals 4 in hydrogen atom? So we need to use Bohr equation. Delta E is equals to RH times 1 over NF square Ni square. Because it doesn't mention electron moves from N1 to N4 or N4 to N1, then it doesn't matter for us. We can only calculate the absolute value of them. Then it doesn't matter if we choose n equals 1 as a final or n equals 4. I put n equals 1 as a final and n equals 4 as an initial. Then delta E is equals to negative 2.18 times 10 negative 18. In parentheses, for final we have 1, so 1 square or just 1. And for initial we have 4, so 4 square or 16. So inside the parentheses, 1 over 1 is just 1, 1 minus 1, 16. Then times the Rydberg constant, which is equals to 2.04 times 10 to negative 18 joules. Let's have more examples. Here in this example, we would like to calculate the frequency of lights that is emitting when the electron falls from level 5 to level 1. So first we need to calculate the energy difference between level 5 and level 1. This time in this question, we know what is initial and what is final level. The electron falls from level 5, so this is initial, and N1 is final. So delta E is equals to Rydberg constant times 1 NF square, which NF is equals 1, minus 1 NI square, which NI it is 5. 5 square is 25. And 1 square is 1, and 1 over 1 it is also 1. So inside the parentheses we have 1 minus 1/25. The value of this subtraction is 24 over 25. So delta E is equals to negative Rydberg constant times 24 over 25, which is equals to negative 2.09 times 10 to negative 18 joules. This is the energy difference between level 5 and level 1, and it is negative because we have emission. This energy is also exactly equals to the energy of one photon. We know the energy of photon is equals to h nu. So instead of E, we can put its value, but we don't use the negative sign. We only use the absolute value. 2.09 times 10 to negative 18 joules is equals to H, or Planck's constant. It is 6.626 times 10 to negative 34. And we want to calculate the frequency times nu. So nu is equals to 2.09 times 10 to negative 18 divided by 6.626 times 10 to negative 34. The answer is equals to 0.315 times 10 to positive 16. And if we write it in scientific notation, we have to move the decimal and write it in this form: 3.15 times 10 to positive 15 hertz. Here in this example, we would like to calculate the wavelengths of photon when electrons falls from level 7 to level 2. And because we have R value, so it's a lot easier to use the Rydberg equation instead of Bohr equation. So Rydberg equation is 1 over lambda, it's equals to R 1 over NF square minus NI square. So initial is 7 and final or destination of electron it is level 2. So the value for R is 1.097373 times 1 over NF square. So NF is 2, so 2 square, or we can just write 4 minus 1 over Ni square, and Ni is 7, so 7 square, or we can just write 49. Then 1 over lambda is equals to, again, 1.097373 times 10 to 7 times 1 over 4, it's 0.25, and 1 over 49 is 0.0204. So the value for 1 over lambda is equals to 2.52 times 10 to positive 6. But we need to find wavelength or lambda. So we need to flip this equation, and lambda is equals to 1 over 2.52 times 10 to positive 6, which is equals to 0.397 times 10 to negative 6 meter, or we can write 397 times 10 to negative 9 meter, and we know 10 to negative 9, it's called nano. So the wavelength of the radiation, it is 397 nanometer. And here is the last example. In this question, we would like to calculate the energy of photon produced when electron falls from level 3 to level 2, but not in hydrogen atom, in helium cation. So Bohr atomic model, it is not only for hydrogen atom. It can also be used in hydrogen-like ions. What is hydrogen-like ions? Ions with only one electrons, like helium, positive, lithium, 2 plus, beryllium, 3 plus, and so on. But Bohr atomic model cannot be used for multiple electrons species or atoms, like helium atoms or lithium atom. The energy was negative RH times Z square over N square. So in hydrogen atom, because the charge of nucleus is 1, we don't have this Z square, we just have 1. But in helium, the charge is 2. And when we subtract these two equations, our Bohr atomic model will be in this form. Negative RH Z square times 1 over final square and 1 initial square. In hydrogen atom, Z square is 1, so we don't write. Here in helium, because Z is equals to, we need to use the Bohr atomic model equation in this form. So the delta E is equals to Rydberg constant, which is 2.18 times 2 negative 18. Z square is 2 square, which is 4. And our final, regarding the equation, it is 2 square, and initial level it is 3, so 3 square. So we have negative 2.18 times 10 to negative 18 times 4, and the value for parentheses is equals to 0.139. So the final answer is equals to 1.21 times 10 to negative 18 joules. Thank you for watching this video. To watch more video, please make sure to subscribe to our channel.